Okay, everybody. It's 6:05 p.m. and we still probably will expect a few more people to hop on the call, but I'd like to kick off the meeting now, just in the interest of time and just to get going. So good evening, everybody, and welcome to IEEE Computer Chapter Toronto Section meeting for October. Very happy today to have David Fisher. He's a distinguished lecturer from IEEE Computer Society to give us what I hope will be a very interesting presentation. And I just would like to kick off the meeting with a very short presentation about IEEE Toronto Computer Chapter, who we are and what we're doing. Let me just share my screen. Just give me a second here. Eunice, you guys can see the screen?
Yes, we can see it.
Thank you. Okay, so good evening and welcome. For those of you, I guess we're all IEEE members, so I don't know if I'm preaching to the choir here, but for those of you that did not sign up or found out about this through other channels, IEEE is the world's largest technical society. We publish most of the leading literature and technology in the world in our field. A lot of the standards have come through IEEE. So it's really a significant organization, makes a significant impact in the world of technology. The Toronto section, there's just a little bit of information about the Toronto section. We've been active for about 120 years. It's the largest section in Canada, 4,000 members in the Greater Toronto area. Many technical societies are represented in IEEE Toronto. So if computer is, obviously you guys are here because you're computer chapter members, but there's lots of other technical societies that are represented in Toronto, and they have regular meetings. We have student branches in all the major engineering schools in the GTA, and our events are found on the web link shown at the bottom here. So IEEEtoronto.ca/events. So myself, my work during the day, I work as a principal technical training engineer for a semiconductor company called Microchip Technology. My background is in embedded systems and Internet of Things applications. Eunice is our vice chair. He works for a company called Munir Precision Monitoring. His background is in IT infrastructure and wireless design and support for field instrumentation monitoring systems. Very interesting work. And very happy to announce we added Peng to our team here earlier this year. Peng is our secretary. He's a senior staff scientist at Huawei. His focus is computer vision research, and he's actually going to be presenting our November technical presentation. So we're really looking forward to that. The Computer Society, I believe, is one of the largest technical societies. Lots of resources to engage with you, and whether it's conferences or standards groups or magazines, technical journals, really lots of resources to keep you up on top of your technology. And like I said, upcoming local events, we have another meeting in about a month's time called Opportunities in Deep Learning, Commercialization and Career Paths. So Peng's been working in this field for a few years, and he's going to share some insight, and we hope those of you who are available, you might want to sign up for that. And look at the events page, you see the registration link for it. So again, we got a lot of social media feeds. Eunice posted the YouTube channel that IEEE Toronto section maintains. So this presentation, this meeting and other meetings are published there. And hopefully you have a chance to check it out. Okay, so I'm going to stop sharing. And David, I'll turn it over to you. And I would say for everyone else, so if we're going to just leave it, if you can keep your microphones muted and your video muted. And if you have a question for David, just unmute yourself whenever you have the question. Just unmute yourself, ask the question. We want lots of interaction and questions, and that's how we're going to run with this. So David, it's up to you.
Okay, do you have, how do I change this?
Click the desktop too. Yep, and then share.
Does that help?
Yes.
Okay. Okay, well, software problems been around for a long time. And I'm not going to say a lot about AI, except that I think it's not going to be a big help to solving a software problem. Oh, aha. Okay, so what kind of motivated this talk? I was thinking back at the Industrial Revolution and how powered machinery, first industrial revolution, really changed the world. And then the enhancements from the second industrial revolution, when we had practical railroads and electricity and gas. The gentlemen here are probably not the ones most of you would put there. But I included George Westinghouse because Westinghouse was really an engineer who made railroads and electricity and gas, all three, practical. In any case, the effect of the Industrial Revolutions was to amplify the speed and reliability and applicability of human manual skills, abilities. And that really led to almost everything you see in society now, including the middle class and the job specialization, and fundamentally changed the economy, society, and science itself. So got the wrong direction here. In the early 1960s, a lot of us in the computer field felt that we were going to see the same analogous thing in an intellectual revolution caused by general purpose digital computers. And in particular, that they too would amplify the speed and reliability and applicability of human, except in this case, reasoning skills. And that would enable improved understanding and invention and reasoning efficiency and movement towards a technological society. And again, dramatic changes to everything. The reality is that didn't happen. With some exceptions, the state of the art in 1970 is not that different than it was in 2022. And yes, we got the dramatic improvements in hardware speed and capacity, but software still has extreme problems in reliability, opaqueness, incomprehensible by its users and authors, difficult to maintain. And I think that's led to exaggerated and unjustified and unrealistic claims about the quality and functionality of software. I don't know if any of you recall, but in the late 60s, the community was talking about what was called the coming software crisis, where we expected that expectations would be so great because of hardware improvements and lack of software to accompany that, that nothing would work. Well, all the things that we predicted for that software crisis actually occurred, except that there was no crisis. The world came to accept software in its current state. Nobody expects software to actually work. Nobody is surprised by bugs. Nobody gets upset with products that don't meet their specifications. And probably a more important thing is that if we look at the four things that computers traditionally were limited to, namely automation of paper management tasks, numeric computation, real-time process control, and modeling and simulation. Those are really only the 4 applications we have today. But what we don't have is any general purpose reasoning support. We don't have what I would call an intelligent interface, which would include natural language. We don't have automated synthesis of programs in any form. And cause or effect, I'm not sure, but products are built with ambiguous and contradictory requirements. We do this without proof or validation. There's a tendency in the academic community to focus on correctness of software, which is neither proof nor validation, but rather actual implementations matching their specifications. And finally, and this I'll be talking a lot more about, the use of unsound logic. Digital computers, the mathematical foundation of digital computers is first order predicate calculus, which is an unsound logic. But I can't. But I'll say a little bit about where AI fits in this. I think the point before AI is that it's a state of affairs in which things are not what we would like. And that means that exaggerated claims and over-optimistic claims are good in any domain. I mean, so what happens in AI is simply, I think, it's a domain that has at least historically exploited that opportunity. And secondly, with AI, we get often a promise that we will do something that everybody knows is hard and everybody would like, and then a claim that an unjustified claim of that extrapolates to anticipate those initial successes to rather ridiculous claims, which I will talk specifically about ML in a minute. On the other hand, you know, the things that AI is trying to do are things that you know, there's general public support and recognition of the value if they were achievable. I just mentioned here a couple of historically AI projects that have not led to either fulfilling their promises or to foundations that other people have been able to build on. The general problem solver, 59, expert systems, enormous investments in expert systems. Natural language understanding, semantic web, and finally, as I think all of you know, if you want to sell a product today, you have to claim it's AI. Okay, AI/ML story. And it's, I think, a story of solving all the world's problems in 4 easy steps. The first one is machine learning. And that is a matter of moving from programmed solutions without learning to supervised automated statistical learning. And that is new and that is different. And I think that's going to have a long lasting value. And then we have deep learning, which is basically moving to unsupervised automated learning and with improved performance over time. These are not my statements. These are ones I pulled out of the literature. And I would only say, how are we going to do that? And then if we had that, then we can have theory of mind, where we get AI will understand human thoughts and interact with humans in a reciprocal learning relationship. And again, I'm not sure how we get from deep learning to that, or how it even helps with deep learning. And then we have self-aware systems. And again, you know, it's a claim of we'll gain human level consciousness, but it's not clear that we have a path. And probably the most advanced AI today, particularly with regard to deep learning, is Watson, the Watson Health product, which, as most of you know, has been sold off with $4 or $5 billion investment to enable that sell. IBM says they made a small profit on it. We hope. I think the general feeling in the AI community even is that this really is a system which does not meet the hype that was associated with it. And finally, again, to repeat, I'm not against machine learning. I think it's actually a, here's the definition I came up. It says it's a stochastic sensory pattern-based learning process, not previously available. It can be valued for situations of uncertainty. That's because stochastic and statistical processes basically can't guarantee results, but often can produce effective results in situations of uncertainty, where you don't have reliable data or you have conflicting data. What I hope it's not used in is in safety critical situations. Heuristics and list processing, I think, are two fallouts from AI historically that are likely continue to have long-term value. Okay, and I just listed a few AI claims here. Some of these are before the creation of computers, but there were a lot of claims about artificially intelligent devices. Gerber said that he created artificial life, including human life, in 800 Christian era. There are claims of using magnetism and sperm and alchemy to create an artificial man. And another clay man brought to life. Well, these are pretty outrageous, but they're not that more outrageous than some of the things that we currently claims that we get. Okay, John McCarthy, sometimes credited with coining the word artificial intelligence, said that every aspect of learning and any feature of intelligence can in principle be described so precisely the machine can make it, can be made to simulate it. Maybe, but we don't have any evidence of that. And it's been a lot of years since John said it. Okay. So, oh, and here's a Forbes magazine, May 5th of this year. And there's parts of this statement that are actually accurate, but I think misleading. In any case, AI enables an unprecedented ability to analyze enormous data sets and computationally discover complex relationships and patterns. And AI augmented by human intelligence is primed to transform the scientific research process, unleashing new golden age of scientific discovery in the coming years. I guess, don't we hope? Let me go backwards.
No, it's too far.
Keep going backwards here.
Yeah, we'll go there.
There we go. Okay, so let's forget all this and go back to the original problem we had, namely that computers can't emulate human reasoning processes. And at least from a logic perspective, there's two main reasons for that. First, logic computers is not sound, and we'll say more. And finally, the logic of computers is really radically different from that of human deductive reasoning, which is probably why I think that we're not going to get there from AI, because AI is still basically a computer program in a traditional sense. Okay, so solution approach. So I have my my magic 5-step process also, I guess. So basically develop a human deductive reasoning like language and processor by characterizing the logic of computers as classical logic and its inherent deficiencies that we would have to overcome, and by characterizing the logic of human deductive reasoning and assume that the human evolution got it right. That is to say, we're not going to do a lot better than the logic of humans. And then develop a new logic that simultaneously emulates the known characteristics of human reasoning and overcomes the deficiencies of known deficiencies of computer logic. And finally, we implement a processor based on that. Well, yeah, this is pretty far out, I guess. However, we know what the limitations of classical logic are. And starting in 1984, I guess, when I was a PI on a DARPA project that was looking into what future programming languages look like, I started working on this human deductive reasoning question. And so I've got 35 years or so of work on that. So let's see where we get to. Classical logic. Okay, so what do we know about classical logic? Okay. Classical logic was an idea of Aristotle, maybe 350 BC. He basically said that there's three laws of thought. No proposition can be both true and false. Every proposition is either true or false, and everything's equivalent to itself. And I think these are all pretty obvious. Unfortunately, they're not true, at least not the law of the excluded middle in classical logic. In the late 18th and early 20th century, philosophers, mathematicians really formalized classical logic into what we currently call propositional calculus or first order predicate calculus, which is just propositional calculus with quantifiers. And that process really had to do with resolving ambiguities, eliminating certain paradoxes, and added some mathematical formalism. Classical logic in this form is, in fact, what we're taught in school, and it's the mathematical foundation of computing. On any logic or any deductive logic, we have two measures of success. One is deductive arguments is valid if and only if it's impossible to have a false conclusion from two premises. And it's sound if it's valid and the premises are also true. And we're going to diddle a fair amount with both of these. So classical logic is monotonic, which is good because it says that proofs are permanent. That is to say, you can't add new consistent axioms and get a, you can't add new data that will change your previous proofs. And classical logic is sound for and valid for domains simpler than natural numbers. Well, unfortunately, almost none of the hard problems that we want to deal with are simpler than natural numbers. And finally, classical logic allows indirect proofs. And without indirect proofs, proofs get very, very difficult. Okay, what's bad is that paradoxes are inherent in classical logic. Logic is unsound for any complex domain. And I would say, at least relative to human reasoning, that meaning is external to the system of the logic. That is, it's a extensional logic. And it depends on truth. That is, there's an assumption that we're proving that things are true. Answers questions about individual things. So I'll just take a couple of these. The inherent of paradoxes in classical logic. Paradox is an inconsistency that we can't prove within the logic itself. And some examples are things like the set of all sets cannot contain itself. Actually, it can't, right? If the barber is the person who shaves the beard of all the men in the village that do not shave themselves, then the question is, does he shave himself? And if that's true, then it's false. And if it's false, it's true. The enemy of my enemy is my friend. Same thing. And I actually prefer, as probably the shortest paradox, this statement is false. If it's false, it's true. And if it's true, it's false. the point is that in classical logic, in computer logic, we can't actually detect, the logic itself cannot detect these paradoxes. While on the other hand, you and I look at these and we say, yeah, we see that this is not right. There's a problem here. And so these are things that are easy for humans to do, but are not within the range of classical logic. The unsoundness of classical logic, that really came up in 1931 with Gödel's incompleteness theorems. And it basically is showing that, well, what incompleteness means is that you can prove false things from true premises. But it arises because of the law of the excluded middle, which, you know, again, goes back and says every proposition is either true or false. And what Gödel said is actually there are propositions that are neither true nor false. So the two theorems he had, the first one is that any domain more complex than integers, actual natural numbers, has truths that are unprovable. And thus so we have unprovable theorems, therefore there is propositions that are neither true or false. And the second theorem said that we can't prove, such systems can't prove their own consistency either. And we're going to try to get around some of these. Okay. Do it again. Okay, and just I won't dwell on this one, but classical logic is extensional, which means that like most logics that we've encountered in computers, the mathematics you did in school, logics of this form are pure symbol manipulation systems. When we do a proof, we're actually just manipulating symbols. But the meaning of those symbols is not inherent in the symbols. The meaning resides in the human oracle, an external human oracle, based on the consistency with the, i.e., you, the interpreter, are the oracle in this case. So what it means is what you say it means externally, but that has to be valid interpretation. It has to be consistent with the domain, that is the symbol representation has to be consistent with the domain of interpretation. And it means that entailment is not inherent in the proof. Okay, in an intentional logic with an S, it distinguishes intention with a T, misspelled. No, I take it back. Namely, sense and meaning from reference and denotation. So there's what we mean, and there's what we reference it by or denote it by. And as an example of that, at the bottom here, I have Jupiter is the morning star. Jupiter is an evening star. So do the morning and evening stars have the same meaning? And the answer is no, they don't. But in computer logic and first order predicate calculus, they in fact do. Because we don't distinguish between Jupiter, the reference, and morning star, the meaning. It just happens that Jupiter is both of these. So in an intentional system, meaning resides in the patterns and relationships among things and is applicable to any domain whose relationships, what did I say there? I don't know what that sentence says myself. Okay, so meaning is in the relationships among things. That enables analogy and metaphor. Think about metaphor. The real meaning of a metaphor is not the domain that it's associated with. It's the interconnections in that domain, which can be applied to a different domain as an analogy. And if I didn't say it before, what we're talking about for human logic is an incomplete logic. That is one in which we don't have a full set of axioms. The things that got us in trouble for complex domains. So what it means is that any description that you have of any thing is going to be incomplete, and that therefore it does not just describe that thing, it describes a category of things, all which have that particular set of properties. And what that means in human logic is that a proof of anything actually applies to a number of different anything of that category. And that leads to possible multiple possible semantics for any given system. Okay, human deductive reasoning. Long list of things that characterize human deductive reasoning. I've listed several of them here. Main thing to note is that these are not things that computer logic, first order predicate calculus, or AI, for the most part, address at all. So first off, human deductive reasoning is a calculus of types rather than propositions. That is to say, when we talk about things, the words we use, let's take nouns. A noun in computers or logic, classical logic, typically refer to either individuals, individual values, or variables that contain an individual value. They do not in human logic, the words we use, the nouns in particular, refer to categories. We talk about dogs or cats. Those are categories. Our noun words refer to categories. Even when we have a proper noun, John, we think of that as naming an individual, but the reality is it names a category of those people who have all the properties that we know John has. So even in that case, we're reasoning about types, concepts, rather than individuals. Thing that got first order predicate calculus in trouble as the basis for mathematics, which it can't be, because the set of all sets is not consistent. Well, the concept of all concepts, it turns out, is consistent. And it's because concepts are not sets of things, they're sets of properties. And they refer to examples of the concepts, which are all those things that satisfy that set of properties. In human reasoning, we deal with consistency rather than truth. Even when we say we're dealing with truth, we typically are not. We don't really mean that. We mean that consistent with all the things that are in the current domain of discourse. It's why humans, for instance, can have not just talk about and represent and reason about the real physical world, but also about imaginary worlds. Okay, devoid of paradoxes. As we illustrated earlier, we can detect paradoxes quite easily. Intentional meaning, we just talked about that. Incomplete. There are things that are unknowable, and that includes axioms, properties of any complex domain. Human logic is valid. That is to say, false can't be proven from consistent, not constant, properties. Logic is sound for all domains. And that's not, humans make mistakes in their reasoning, but it's when we don't think hard, it's when we're fatigued. It's not because of deficiencies in our logic. Okay, let's talk about language a little. Human deductive reasoning requires an informal language. That is to say, formal languages are actually inadequate to represent the ideas, the concepts that we want to represent in human logic. Abstraction, specialization, generalization are primitive operations that, at least in my mind, are the most powerful operations we have in human reasoning. And yet they're operations that do not exist and cannot be defined in terms of things that exist in first order predicate calculus or in computers. How do you do abstraction in predicate calculus? What is an abstraction? It's a broader domain. We could extract from people to all living things. So we remove some of the special properties that people have that all living things don't have, and we get a broader domain. But that's not an operation. It's not an action that can occur in predicate logic, propositional logic, either one. So And to me, abstraction is the simplest thing there is. It says if we have a type or a concept, and we remove some of its properties, some of its constraints, we get a more abstract concept. And that's an operation that's always free. It's never doesn't require any additional proof. And so it's basically removing an item from a set. Specialization is the opposite. We're adding additional properties to a type or a concept. And sometimes we have to prove that that's valid. Generalization is, again, another operation that we clearly do as humans, but is not even a concept in first order logic. Humans use story and, in human existence, stories and analogy are pervasive. They do not exist in first order project or predicate calculus. They're not a concept of computing. And finally, and I think this is important, if you look at computer proofs, they do have an exponential cost in the number of properties, number of propositions that are involved. It always bothered me that graduate students would be doing formal proofs on a computer, and the computing times were in hours and days, and they were things that you or I could do in a few minutes by hand. So it was clear to me that there was a significant difference between the methods of human reasoning and the methods of formal logic as we know it. Okay, how am I on time? Dennis, we want to worry about time at this point?
We're good. It's 10 to 7. We're good.
Okay.
Like I said, if anybody has questions or would like to interject your thoughts or have a question for David, just unmute.
I'm about 3/4 of the way through this too.
Yep.
So
yeah, we're good. We're good.
Okay. So what happened is that I, in my spare time from 1984 until about 5 years ago, was trying to develop this logic. And on my original DARPA project, we failed. We just could not do this. And we knew the key to it was that types or concepts had to be self-describable. That is, the type of all type had to be consistent. And I really didn't get that until 2017, probably. So anyway, so here's a long, I guess, description of the logic of property-based types. It basically says it's a calculus of concepts or types. That is to say, it's a higher order logic. Types are sets of properties that represent concepts. And what that means is that a property is a relationship among types. Well, there's really three parts. So the type is a set of properties. And a property is a relationship among types. And an example of a type is any individual, anything that satisfies the properties of the type. And if you've got those three, you've got basically the essence of what a property-based type is, or concept, if you like that word for it. Interestingly, the examples, the things that satisfy all the properties of a type, are not, in fact, part of the logic at all. So if we have dogs, we have a bunch of properties that describe the type dog. Anything that satisfies all those properties is, in fact, a dog. Nevertheless, individual dogs are not part of the logic of human reasoning, and in this case of property-based types. And the type of all types is consistent. And as we said, that was our enabling feature. The reason type of all types is consistent is because types are not, in fact, sets of their examples. They're sets of properties. And it's only indirectly that you get to the examples from the properties. I.e., I can actually describe the properties of types, and that is in fact itself a type, and it violates none of the rules of types. Okay, it's a logic of consistency and not truth. It's devoid of paradoxes. I think we got a slide on why. Meaning is intentional. We talked about that, and maybe a little bit more. Incomplete. All domains are assumed to have unknowable properties. And yes, there may be some names, some domains for which we know all the properties, but we don't make that assumption in the logic. Okay, so that means that we answer questions about categories of things rather than the individual things. We already talked about that. Valid for all domains, as is human logic. Sound for consistent domains, as is human logic. Interestingly, we do have a law of the excluded middle. But it's for consistency rather than truth. So it says that every type is either consistent or inconsistent. There's nothing that is neither consistent or inconsistent. But that only works because types are finite, well, at least countable sets of properties, where in logic of computers and propositional calculus, we tend to think of the types or the concepts are things for which we only know some of the properties. And the answer is no. A type here is, the concept here is a fixed size set. It has no, the type has no additional properties that we don't know. Individual examples might, but they're not, they're outside the logic. Okay, monotonic. Yeah, if we prove something, it stays proved. It doesn't go away because we got new information. Very, very unlike, say, machine learning. Requires informal language. So why do we need an informal language for PBT? Why do we need an informal language for human reasoning? And the answer is that we're dealing with incompleteness. And that means, you know, every linguistic form that we have, everything we want to talk about in the logic is either incomplete or imprecise or vague or some combination of them. We never tie everything down. And that means we need a language in which we can express incompleteness and impreciseness and vagueness, as natural languages are quite good at. So words name types, we mentioned that earlier. We also have modifiers that name properties. And sentences name assertions or questions. Okay, abstraction, specialization, generalization are primitive operations in this logic. And that simply means that we have a set of, if we have a set of properties, a type, and we abstract from it, we remove some of the properties. If we want to specialize, we add properties. If we want to generalize, we actually remove properties from parameters to a function, and that generalizes the function. Steroids and analogy are essential in this logic. And why is that? Well, they're essential for reasons of performance. It turns out that we were talking a minute ago about if I prove things in using computer logic or bracket calculus, the proofs are basically exponential cost. And yet when humans do proofs, we don't have that exponential cost. And what is it that allows us to reduce that cost to less than exponential? And the answer is analogy, which could be tied to stories. And I have a slide on that particular point. So the cost of proofs actually in this logic are near linear, which means strictly less than order n squared. Okay, a little bit on the language. Words in the calculus of types, words name types, not individuals. We already said that. Types are sets of enumerated properties. The number of properties is less countable. The number of types, right? So if a type is a set of properties, and there's a countable number of them, then the number of types is the power set of the number of properties, and that's uncountable. So we basically have countable properties, but uncountable types. And since words are countable, we can't possibly associate a word with every type. So we end up that only a tiny subset of types actually have a word to name them. And that's just the way of the world. So the implication is that we need modifiers in our language to name properties so that we can describe things by a combination of words that name types and words that add additional properties. And so we expect that from all natural languages. Some examples of this is that, well, what that says is that in any language, any natural language, in the language of this logic, we have a number of types that we're dealing with, but most of them don't have names. And so if we're talking, say, Japanese versus English, the types, the concepts that actually have an associated name may not be the same. There may not be one-to-one correspondence. And so, for instance, blue in Japanese does not mean the same thing as the obvious translation into English. Similarly with dog in Spanish. Dog in Spanish and dog in English, in fact, do not describe the same type. They describe, they each have a word that we tend to say is the translation, but in fact, they're slightly different. Another implication is that meanings are vague and incomplete because we don't have complete types. Okay, performance. Ah, yes, the question of how can we have exponential, non-exponential time for proofs? Well, we talked about abstraction, specialization, generalization, what they involved. They're just adding and subtracting properties from types, sometimes adding, sometimes without any proof required. Sometimes we have to show consistency when we do that. Okay, so how do we do a proof? Well, instead of just proving it based on all the axioms in some n squared or greater form in property-based types, and we would assume in human reasoning that what we do to do a proof is to move to a more abstract domain. So I'm trying to prove something in a particular domain, domains or types. We remove some of the irrelevant properties and we have a simpler domain, simpler but more abstract domain. That movement is a constant cost. And we could come back to the original domain by another linear cost. It actually turns out, because we have to show that it's still consistent. But we can do then do a simpler proof in this more abstract domain, and it's still a cost that is going to be exponential in the number of properties that we have. But if we abstract sufficiently till where n is less than some constant, any constant you like, then it's order constant squared, which in fact is a constant and therefore not a higher order. All this leads us to, by abstracting, we can do simpler proofs. And we can do those proofs in a way that the total cost of the computation, that is to say, the cost of moving up this hierarchy of abstract concepts. The tree is, concept tree is log n high, and it takes us a cost of n for each step of that. So we get an order n log n for our total costs. And although that's more than linear, it acts like a linear. That is to say, log n acts like a constant, and therefore n log n cost of proofs is less than exponential and looks like a linear. Okay, I probably skipped something there. Yeah, just a quick thing on statements. It turns out that at least by the rules of property-based types, that any declarative statement that you want to make can be of one of 6 forms. I'm not implying anything about order here, but these are the kind of the English correspondence to it, but it should apply to any natural language. It says you have a subject as an object, meaning it's a subtype of the object's type. A subject is a modifier, that is sky is blue. Subject has an object, any kind of possession. Subject with an action or subject with an action and an object, all the action verbs, forms. And finally, there is a subject. These are, in fact, in my mind anyway, the 6 forms of declarative sentences in English. And we can find correspondence in almost any other language. Interestingly, the there is form is the only example in English of a true word that does not have a meaning in English. That is to say, it's necessary to make the grammar work. And what that form is if you think about predicate calculus, it has 2 quantifiers, universal quantification, which is implicit in all aspects of PBT logic, and existential quantification, which is there exists, and that's exactly what the there exists English is. So in PBT logic and in human reasoning, existence is a property. It is not a aspect of the logic. It's a property of certain types. Modifiers, we already said why they were necessary, namely to have a countable number of words. So again, pretty much language independent. Named properties are adjectives and adverbs. Relational properties are some kind of preposition with an object. Quantities, and by the way, this is not quantifiers now, it's quantities, which gives you a subset defined by the quantity rather than the properties. Can be ordinal or cardinal or just vague quantity words. So it's like 7, the third, and many. And then finally, there's definiteness. And that's when we're talking about examples. Do we mean an arbitrary example or a specific example? Or do we actually mean a type and not an example at all? And so there needs to be forms in each language to corresponding to each of these semantics that we want. But again, I think this is, and that's one of the values of property-based types, is that it really gives us a handle on what natural languages have to be and have. And then there's not much left, but there's how do you do questions, and questions really are just they're analogous to declarative sentences, except that each of the types in them has to be interpreted as a free variable. And we have words like in English, like what and why and how and which and so on that allow us to do that. Serve as the free variables. Conjunctions, we need semantic forms for conjunctions of examples and separately of types, and they have different meanings. Negations, units, UNITS, not O, of measure is really from the mathematical world, and mathematical expressions are things we probably would want to add, even though they're not normally thought of in natural language. So I'll just end on this. So basically where I come to is that software validity and human reasoning require a sound logic. Neither classical logic nor AI are sound. And that means computer logic isn't. AI, other than ML anyway, is logically equivalent to other computer software. So what we can do or can't do with AI is the same things as what we can and can't do with computers. First order predicate calculus, computers, AI, and ML all have very little in common with human reasoning. PBT is an example of a logic that's similar to human deductive reasoning. And PBT helps explain a language, aspects of language and human reasoning. In fact, that's my main method now of testing whether it's credible or not. That is to say, does it explain these things about why natural language is the way it is and why we're able to, say, do proofs in our heads that we can't do in computers because of the costs. And I'll stop with that.
Yeah, what an interesting presentation. I mean, it's not often speak for myself. They just kind of brought to the foundation of your field, right?
I'm sorry?
Very rarely have I ever sort of considered sort of the foundation of like the logic behind computing, right?
Right. No, we don't.
Programming languages. As a practitioner, it's just so I just haven't really thought about this in a long time. So very, very interesting presentation. And so that's your statement here. AI is logically equivalent to other computer software.
Yeah.
Anything that says it's AI is really, it's an implementation of standard. It's just standard code.
Much. And like I say, ML is a little bit different because it's really using, it really has to do with input output, if you think about it. ML can do the things that animals can do that computers can't. In fact, it's kind of it's kind of what's left when you take out of humans the part that is distinctively human. But this thing about not thinking about the logic when you're in your everyday life, it strikes me that if you're claiming to be AI, then what you're claiming is that you're going to end up with an intelligent capability at some point. Mm. That says you've got to be thinking about the logic. And that's what bothers me probably the most is that the AI people, more than the traditional computing people, ought to be looking at the question of what is the logic of human thinking? How does our logic differ from that of first order predicate calculus, for instance?
Yeah. This PBT logic that you were working on, was there any I hate to use the word like kind of an implementation, or was there a way to sort of apply it in I don't think you mentioned it, but it didn't get sort of implemented in kind of we'll call it a programming language, or a way of solving some practical problems using this reasoning?
Yes, that's how I spend most of my time these days, is on the implementation.
Oh.
We actually have a PBT is to a language I'm developing called Omega, the same way as first order predicate calculus is to traditional computing languages. Mm. And so it is a language which kind of has the descriptions I gave you here. It looks like natural language because it doesn't have any choice not to. It has nouns that are types and words that are And so it kind of looks like natural language. You describe things and you ask questions. And those questions may then lead to the generation of a computer program that will actually execute something, or it may just be a application of a PPT proof.
Do you think, so you're saying it could be used to create like a model for a solution that you can then code in a classic programming language?
Yes. If the question you're asking happens to be one that would be reasonable for a traditional programming language. But I'll point out that I said it in a very early slide that modeling and simulation really is the thing of digital computers. What they do is they model things. Even when we're doing, a data processing problem, we're really on a computer, we're modeling that abstract data structure. But those models are always inaccurate because they're incomplete. We can't have both completeness. I can't be both complete and accurate with regard to another object without being that object. So what happens is that when we do simulations on a computer, they involve a model which is not the same as the thing being modeled. And that means it's an inaccurate model.
It's good enough. It may be good enough, right? It might be practically
good enough, but
right?
it also means that there's questions that we can ask of the model, which will give it different answers than ask of the real thing. And furthermore, we have no way of knowing which questions those are in general.
Dennis, we do have some questions.
Yeah. Yes, there was some questions here.
Good.
So a question from one of our attendees. Does PBT allow programs to exist that are more like human thinking?
I'm not sure quite what that means, but the answer is that there is a proof engine for the PBT logic. And so if you ask a question, you should either get an answer we'll always get an answer, but it might be that it doesn't have enough information to answer that question. In fact, that's the standard non-response response from the PBT logic. It says, you ask me something, and if I have enough, if it can be answered from what I know, then I will give you an answer. If I need more information in order to answer the question, remember, because this is a logic that has basically consistent, inconsistent, but if it's consistent, you don't know if it corresponds to true or false. Probably was not clear on that at all.
Any other questions? Again, just I would ask if you just unmute yourself and just if you have any questions for David. Was your contact information on the first slide? I can't remember your email address or just if any of our attendees would like to reach out to you. Oh, there you go.
Yes.
Here's your email address. Okay. There's
an email and a postal address. I guess.
And what's your background? I'm sorry, I didn't, I guess, ask you to, when you kicked off your presentation, maybe, I guess some of us would be, what is your background? Like we can see your title here. You're an emeritus professor, and what was your career like? And I think you've more kind of explained a bit here and there through the presentation. But.
Sure. Undergraduate in mathematics, but mostly interested in computing. Really lucky to go to Carnegie Mellon as an undergraduate back before computer science was a field. And so I, as an undergraduate, took all these graduate courses that were taught for the first time when they were trying to create a PhD program in computer science. Master's in EE, PhD in computer science from Carnegie Mellon later. Did a little bit of everything, never an academic really, even though I spent 19 years at CMU in various capacities. Sometimes took sabbaticals for a couple of years with the government. So I was an executive in the Office of Secretary of Defense for two-year periods. I was an executive in the US Department of Commerce for 2 years. Always doing computer-related things, but sometimes in high-performance computing, sometimes in programming languages. Myself as a technologist, I would basically say I'm a programming language person. I've designed half a dozen or so programming languages and built compilers for them and did a lot in compiler construction. But having spent 19 years at CMU, mostly at the Software Engineering Institute, people think I'm a software engineer.
The compiler is just the silent workhorse. Yes. The silent workhorse of modern society. Yep. Yeah.
So I have a question.
Yes, please go ahead.
And I was the one that asked the PBT question too. However, I guess it's all good stuff and it sounds pretty exciting, but I guess at the end of the day, does it actually, in some distant future, lead to something that could help solve this question or this statement that's right in front of us right now? Like, will it help software to fail less? And does it provide the possibility for a better version or a more powerful version of AI?
Okay, I'll answer that. I'll answer your two-part question in 3 parts. The problems we have with software, I think, ultimately go back to the fact that we have an unsound foundation for computers. And that leads to inconsistencies, and therefore anything goes ultimately. We used to always try to prove the correctness of programs, and now programmers don't seem to have any, or their sponsors seem to have any interest in that. We expect bugs, software will have bugs, and that's the way it is. Well, I think if we go to a sound logic as a foundation, then these software failures are going to disappear. So I think yes on that one. As far as the AI, I still take the position that almost all, if not all, of AI is the same as software. It has the same problems, the same solutions. They're really indistinguishable. And the other, which I think you're implying at, is that, are we going to be able to solve the AI problem? And if the AI problem is to build machines that reason like humans, that is to say, substitutes for humans, I think the answer is probably no. I hope so. On the other hand, are we going to build something that I can really use as a reasoning assistant to help me reason more clearly and faster and so on, and amplify my ability to reason, particularly in fields that care about validity, like science, then I think, yeah, that's going to happen.
So then you would not bet on this thing anytime soon?
I don't know. I really don't know. I'm really anxious to get PBT and omega to a shape that I can really run experiments with the product. But even if I don't get that far, I think I'm already, for instance, for my talk, I said a lot about natural language. What I said about natural language was why it has to be the way it is. I don't think that people doing natural language research have those answers yet, and I just gave them to you. It provides a new foundation on which people can do natural language research. Right now, they're floundering a bit because they don't have anything solid to base it on. Schenck tried this. I'm sorry, not Schenck. Chomsky, and he just couldn't ever quite get there. So I think there's going to be some value in it. I just don't know how far it's going to
go. Are other people taking up your cause?
Not as many as I'd like. Probably through my own fault. I haven't been very. I haven't publicized it very highly at this point. Probably too much of a perfectionist, but yeah, that has to change.
Thanks, Don. Good question. Any other questions?
If anybody would like to participate in this, I am looking for collaborators. I even have funding for collaborators at this point. Mm-hmm. You don't have to be an academic. You just have to be somebody that enjoys working on these things.
Mm-hmm. Okay. Well, if there isn't any more questions, I guess on behalf of our chapter, sorry, and all the folks that are on the line tonight, I'd like to really thank you, David, for sharing your work with us and sharing this interesting presentation.
Okay, thank you.
Yeah, and for everyone on the call, we'll, like I said, this is being recorded, and going to do a little bit of editing to take out some of the chatter in the beginning of the session, but this will be posted on the IEEE Toronto section YouTube channel, I would say within the next week or so. And if any of you have questions or you want to reach out to myself or Eunice, we gave our contact information earlier in the presentation. And thanks, everyone. Thanks, David, for joining us. And thanks, everyone. Have a great rest of your evening.
Okay, thank you. And if anybody is interested in following up on some of the discussion, I certainly can do that too.
Great.
Thank you, David.
Yeah.
Thanks, everyone.
Thank you.
Yeah, thank you. Good session.
Thank you. Have a good night. Thank you.
Yep. Bye, everybody.
Bye.